Today, I'll be talking to Dr. Ellen Zhong, a computer science professor at Princeton University. Ellen's research focuses on applying machine learning to protein structures derived using cryogenic electron microscopy, also known as cryo-EM. In fact, she was one of the first people to ever apply deep learning here, and her lab at Princeton remains at the forefront of this field. Today, we'll be talking about her research, what the future of protein structure determination looks like, and her recent sabbatical at Generate Biomedicines. Thank you for coming onto the podcast, Ellen.
Yeah, thanks for having me.
So my first question is, I gave a very brief overview of what your own personal research interests are, but I'd love for you to give your own take as to what you're most interested in these days.
Sure. Yeah, so right now I'm a professor of computer science at Princeton University, and our group works on various molecular machine learning problems, so really kind of interesting problems at the intersection of AI and biology. And specifically, we focus on structure determination. So can we actually analyze actively collected experimental data, in particular cryo-electron microscopy or cryo-EM, to solve the actual 3D locations of the atoms of these macromolecular machines and be able to understand how they work and discover new kinds of proteins and their dynamics.
When you first got involved in this field, like back in your PhD days, it seemed like you were the first person to ever take like cryo-EM particle images and apply deep learning there. When you were doing that back then, did it feel like you were taking a really big risk, or was it kind of like you were kind of sure of yourself, like this was the right direction?
I guess at the beginning of my PhD, I worked on a couple of different things, and then I learned about the cryo-EM problem. And I thought this 3D reconstruction problem was really interesting. And in particular, this problem of reconstructing continuous motions was unsolved at the time. And actually, I was sent this paper by Roy Lederman and Emmett Singer, who are mathematicians at Princeton University, about kind of this mathematical kind of introduction to this problem. And after reading that paper, I was like, whoa, this is a really cool problem. And I guess I didn't know at the time that the rest is history, but it was very much like, this feels like a problem, a very juicy problem that I can work on for, the next like 5 years or something like that. And I didn't really think about anything else. But when I, at the time was learning more about kind of modern machine learning techniques, it seemed very natural to apply these deep learning models, which can learn super complex distributions from large scale data sets, to this cryo-EM problem. But yeah, it was super fun.
When it comes to actually like applying machine learning to cryo-EM particle images, I have a vague sense of what that means. Would you be able to give like a brief overview of what it actually means to take like the cryo-EM particle images you get out of an electron microscope and throw ML at it?
Yeah. So the specific problem that was the focus of both my PhD work and is very much a central research question in our group right now is this 3D reconstruction problem. So the electron microscope, you take a bunch of 2D projection images of your vitrified or flash frozen biological sample. So you have a bunch of 2D pictures of your protein. And then there's the kind of algorithmic challenge of reconstructing the 3D structure from all these 2D particle images. And so it doesn't have to be approached, with deep learning approaches. There's a lot of like classical algorithms. There's state-of-the-art tools that are, not using neural networks to do this 2D to 3D reconstruction problem. And the kind of central computational challenge is inferring both the 3D structure, but also the unknown camera poses and orientations of each of the molecules. And the specific kind of new challenge we're interested in is what happens when the different proteins are in different conformations. So not only do we want to reconstruct the 3D structure, like kind of a static picture of the protein, but we want to reconstruct kind of a movie of the dynamics of these macromolecules, which, to me, that seemed like the coolest thing, right? Structural biology was, it's already so interesting to be able to see these 3D structures, but can we actually see like how they work and how they function from experimental data?
I've written about cryo-EM before, and it seems like there were 3 distinct phases to the field, at least the part of the field that you work in, where at the very beginning you're focused on ab initio reconstruction, where you have no prior knowledge as to what the actual protein structure looks like. Then conformational heterogeneity, where there are multiple conformations in the particle images. How do you like tease out all the possible conformations? Before I get to the third one, before we get to the third one, for ab initio reconstruction, is that a solved problem? Like you no longer need to have any prior knowledge?
For well-behaved samples. So because this is like always kind of collecting active new experimental data, you need to like solve this 3D reconstruction problem for every single protein. And so for these like kind of new complexes that people had no idea what they looked like before, there's like so much upstream work, both to like make sure the sample is like expressing well and like well behaved, make sure the ice is like very kind of thin and you can have like high quality images. And then there are existing methods for ab initio reconstruction. And so kind of assuming that your input data is reasonable, then you can do kind of this pose estimation in 3D reconstruction to get the structure. But that's very much still like a open problem.
Is it an open problem in the sense of like sample prep can mess it up? Or is it an open problem in that even if the sample prep is perfect, there are some proteins which, like cryo-dragon, which is the method you created to solve ab initio reconstruction, it still doesn't work?
I would say both. So like definitely if the sample is not good, the like algorithms are not going to solve that for you. But the kind of part where it becomes interesting whether you can kind of jointly design the experiment and the algorithms are when you have like lots of dynamics in your protein or maybe like a complex mixture of multiple things. If you just have a very purified protein that's like very much like a rock or something like that, or a ribosome, which is one of the like canonical examples in cryo-EM, then it is shockingly easy and absolutely fantastical, like how we can kind of solve the structures of these molecules in like a day.
Before I move on to conformational heterogeneity, one thing I wanted to ask was I saw that you posted on Twitter recently about cryobolts, which is like trying to use existing protein structure predictions. It's like, almost like as like a starting point for the cryo-EM modeling. If you have that, do you even need ab initio reconstruction, or the prediction models are actually like pretty good? And
yeah, that's like another like super interesting question for the field right now. So I feel really lucky that like currently we have like AlphaFold 2, AlphaFold 3, bolts, like all these like really powerful protein foundation models that can just predict structures from sequence. So like, why do we even need to do experiments? And the answer is like, okay, these prediction models are just predictions. There's a lot of proteins where you can't actually, a lot of specifically like large complexes, which are the functional machines in vivo that do these like essential biological processes. So for those, you can't like predict the entire structure.
Sure.
If we want to understand function, if we want to actually be able to see kind of what's going on and the mechanism of these essential molecules, then we still need experimental data. And especially for like training the next generation of these models, we're going to need to understand like what are the interesting actual ensembles or like dynamics and like larger complexes to be able to have these structure prediction models reach kind of the next level.
I'm going to have more questions about that later, but moving on to conformational heterogeneity, that was the subject of cryo-dragon 2, which released in 2021. Is that correct?
So yeah, I should give like a whole talk or something like that. But the cryo-EM reconstruction, so cryo-dragon is our model for reconstructing it's a VAE based kind of neural model for reconstructing these distributions of structures. And at this point, we have so many extensions of cryo-dragon that tackle like more challenging, maybe like settings of the problem or in situ data with cryo-ET. But in our group, we're just all calling it cryo-dragon to have it in one software package so that people know like where to, I guess, like access the model and where to use the method. The original cryo-dragon paper was tackling, like the original machine learning paper was very much trying to tackle the whole enchilada of like ab initio reconstruction of complex mixtures or of kind of distributions of structures. And then when we were creating the software tool for the actual structural biology community, then I realized, wait, that's actually too hard. And already if we just tackle this conformational heterogeneity problem, where you assume you already have the camera poses and you just want to kind of infer residual heterogeneity, we can already discover interesting things like kind of misstructures, like new conformations, continuous motions, which was the original motivation for the method. That was cryo-dragon, I guess, like V1. In cryo-dragon 2, we revisited this ab initio reconstruction problem to make it.
So conformational heterogeneity came first, and then ab initio came second.
Yeah.
Okay.
So the original kind of iClear paper in like 2019, 2020 was trying to do everything. So it was like, yeah, I guess at the time I didn't know like what the scope was for like a machine learning conference paper. Like, I just want to solve everything.
Yeah.
So that was doing ab initio heterogeneous reconstruction.
Mm-hmm.
And then later when we developed the tool, we kind of like just focused on the conformational inference. And then I guess in my research group in the last couple of years, we've released an extension, CryoDragon ET, to cryo-ET data, and CryoDragon AI, which is ab initio, not artificial intelligence. And those two methods are like, these are designed for modern cryo-EM data sets to actually tackle kind of ab initio reconstruction of like super large, complex cryo-EM data.
So yeah, okay. I guess I mixed the two up in terms of timeline for the conformational heterogeneity bit. Is that entirely solved? Like, given a protein that is very flexible and displays many conformations, if like a cryo-EM person took images of that protein, applied the CryoDragon software package to it, could they reliably grab out all the conformations, or there's still like an ongoing, like there's still ongoing issues?
Yeah. So none of these problems, I would say, are like solved, right? These are all very much like open challenges that any new data set could present like completely new challenges. There are now, I mean, it's an exciting time because there's a lot of like new methods, both neural network based and also kind of, classical kind of signal processing based algorithms or like computational, like numerical linear algebra methods to tackle this like heterogeneous reconstruction problem. But yeah, I would say one of the main challenges is that this like heterogeneity problem in cryo-EM is like not super well defined, right? There's a lot of like, it really depends on what the practitioner, what the structural biologist wants at the end of the day. Like, do they want an ensemble of structures? Do they want an ensemble of atomic models, which is what cryobolts is trying to do, is like this atomic modeling part of cryo-EM.
Sorry, what? I've like in my head, the output of the output of this like is like one singular ground truth. What is the full ensemble of truths out there?
So I break down this cryo-EM problem into where there's like a couple of stages of, I guess, image processing. There's the pre-processing of the raw micrographs, and there's a lot of kind of steps to that. And then there's this 2D to 3D reconstruction problem. So that's already with like kind of segmented single particle images in 2D to resolve the 3D structure or an ensemble of structures. Those structures, so structure is an overloaded word. In the cryo-EM setting, that means a density volume, right? So it's just the electron scattering potential of the molecule as felt by the electron beam in the cryo-electron microscope. And then, assuming you have a sufficiently high resolution volume that's not, filled with artifacts or too low resolution, then typically what's done is you manually build in the atomic model. As of recently, now there's some tools based on kind of these like modern deep learning and like, protein based models that can do atomic modeling, but it's still very much a manual art to actually placing the atom locations to then deposit into the PD.
That is surprising. I kind of always thought I guess it makes sense that the output of cryo-EM is an electron density field because like what else could you possibly gather from like shooting electrons at something and seeing how they like what comes out on the other side on the electron detector. But I also assumed that like assigning atoms is a trivial process. Why is it like intuitively? Why is it hard?
So it's very trivial if the volume is high resolution. So if you have like an atomic resolution volume, then you can just like see where the nuclei are and like place the atoms. But that's extremely hard, and for most, like a high quality cryo-EM structure will be like maybe 3 angstrom resolution, which is enough to resolve maybe like secondary structure features and like some side chains. And then based on our existing kind of prior knowledge on the geometry of protein structures or like nucleic acid kind of structure and composition, then you can mostly kind of unambiguously place the atomic models. But also, I mean, this is just like a messy kind of hard scientific problem. The structures are not necessarily uniform in resolution. The parts that are moving will be lower resolution because, we've kind of blurred it together in the standard reconstruction problem.
So like if there's like a bit floppy over here, it'll just like smear the electron density.
Yeah. You'll smear it kind of together, assuming you're doing a like homogeneous 3D reconstruction. So the whole kind of promise of CryoDragon and these like heterogeneous methods is that we can actually model the ensemble, and then we're not averaging together all these different conformational states. Yeah.
So we've discussed like ab initio reconstruction and conformational heterogeneity.
There's a lot of jargon.
Yeah. One of the I think craziest things you've written about was a paper at the end of NeurIPS 2024 called Hydra.
Yeah, multi-headed dragon.
Yeah, which is a method that I think the phrase used in the paper is compositional heterogeneity, where you have multiple proteins on the same micrograph, and you are trying to like multiplex the structure determination of all of them at once.
Yeah.
I haven't seen this was like back in December 2024. To me as an outsider, that just feels like clearly extraordinary. You're able to like 2x to 3x how many proteins you can like shove through this incredibly expensive and manual process.
Yeah.
Is it as like revolutionary as it seems on face value? Like how much work is there?
Yeah. So it's a very hard problem, and that's very much still what we're working towards. Like, can we do high throughput structure determination, not only of like ensembles and kind of these dynamic atomic models, but just like shove multiple proteins into the sample, into the electron microscope, and then simultaneously solve their structures. So that's very much something that we're still working towards. Hydra, we demonstrated maybe like 3 or 4 different structures on real data at the same time. And it just becomes a much more challenging optimization problem with more and more proteins if we're using like classical like based approaches where we're trying to infer both now the identity of the protein and the pose, or kind of the like 3D orientation relative to the camera pose, so the orientation of the particle within the ice, and also the conformational state. So I think like there's probably some inherent limit to kind of these like classical based approaches. And so very much as like a moonshot in the group right now, we have a bunch of new projects that are like, what happens if we want to solve like 1,000 structures at once?
Yeah.
What happens when we want to analyze a cellular lysate or a cryo-ET sample, which is like a slice out of a cell, and actually like solve all of the
There's like dozens of
proteins
biomolecules in there, maybe hundreds.
Yeah. And that's, I would say, I mean, it's both a good thing and a bad thing, but it's very much still a moonshot, right? And it's very exciting times.
In the paper that was at NeurIPS, there were 3 proteins determined. Is like 3 as of then, like 3 kind of the upper limit, or is it more like we haven't tested up to like 5 or 10 yet? We just like chose 3.
I would say it very much depends on the experimental sample. So definitely people are doing structure determination from like native kind of extracts and things like that, actual kind of like structural biology papers, and using kind of classical based reconstruction methods, you can simultaneously solve like, a handful of different structures. The unfortunate state, like the status quo though, is that it's very manually driven, and it's very kind of like an expert kind of structural biologist or cryo-electron microscopist is like going in and trying to like look at, you're kind of arbitrarily subsetting your data set to find like reasonably pure classes where it's, mostly just one complex or not. And it becomes this very kind of user-driven process. And so even in like kind of cryo-EM papers where you're focusing just on a single structure, if you look in the SI and you look for one of the like data processing figures.
Sorry, what's SI? Oh, supplement.
The supplementary.
Okay,
Yeah. If you look in the supplement, there's always going to be one of these figures that show the image processing pipeline, and it's just this like crazy flow chart of like all the different steps and all the different, like kind of user chosen subsets that are taken to get to the final particle stack. And so very much one of the interesting computational challenges is, can we like automate that process? Can we make it like either like one shot from a kind of algorithm that is trying to do all of the processing or the kind of optimization in one go? Or, I mean, these days, can we have like a like autonomous or like agentic approach to tackling it? So there's so many interesting kind of like directions right now.
What is currently the like in my if I just come at it from like an incredibly naive perspective, if the problem is like, oh, there's like so many, like let's say you're trying to do like 100 proteins in one shot and there are like so
Hmm.
many different conformations each of these unique proteins have, how do you subset them into classes?
Hmm.
My instinctive idea is just like, oh, expand the micrograph and like have more
Mm.
shots as to like,
Just collect more
yeah, just
data.
collect more, like
Hmm.
is it it's just like, yeah, like what's the primary bottleneck in like getting to a
Hmm.
100 shot cryo-EM?
Yeah, I think so the number of images that we're taking right now is like uh people can collect a lot of data. The microscopes are becoming very automated.
Mhm.
So I would say data collection is not necessarily a problem. I think people are not actually actively working on it from like the experimental side, which is interesting. And I
That's, yeah.
think, I mean, there's also like experimental challenges too. There's computational challenges. You really need to do both.
Mhm.
I'm excited to do that. And actually, along these lines, um, my group and the Flatiron Institute and CCPEM, which is this kind of like structural biology consortium in the UK, are putting together this challenge. We're calling it CAHRA, or CAHRA, Critical Community-Wide Assessment of Heterogeneous Reconstruction Algorithms,
Mhm.
where we're collecting data sets of kind of complex mixtures and just seeing how people do with existing kind of methods or workflows.
Up until Hydra came out, or maybe like methods like it, did data sets of heterogeneous mixtures just not exist?
Um, no, I do think that's one of the challenges for the field is like very much people are just working on their bespoke protein complexes and then they deposit the data, but it's not kind of targeted towards like algorithms development
Yeah.
or kind of pushing the capabilities of like maybe like extreme compositional heterogeneity. But
When
that's something that, yeah, we want to work towards.
when people deposit their data in the cryo-EM field, do they deposit like obviously like do they just put the like the electron density structure on the PDP, or is there some
Mhm.
practice of also giving the like ice crystal images?
Yeah, so people deposit both the atomic
Okay.
models and the density volumes. And something that is common but not ubiquitous is depositing the raw electron microscope data
Mhm.
to Empire, which is another kind of publicly accessible database. And that's where things get a lot messier because the raw data is usually like much, much larger, like terabytes of raw imaging data. And, the processing is like challenging. And yeah, I think that's like a major challenge is
So,
like,
so like even if you like, let's say like we lived in a world where everyone like deposited their raw data onto these
mhm.
platforms, even then would be like such a headache to deal with the data that's not necessarily clear that it would translate to all that much utility.
Yeah. And also, yes, both that, and there's no standard like metadata and things like that. So, there's maybe just some like kind of system wide logistical challenges
What?
and the fact that the data quality is very heterogeneous.
Yeah.
And so sometimes you have like really kind of high quality micrographs and other times it's like not that great.
How much is like the generation of the micrograph like almost a skill issue on the person who like actually generated the data versus
Hmm.
like there are just some proteins that are very difficult to like characterize well, and the data will always be low quality.
Hmm. Um, I would say both,
Okay.
right? Yeah. Like this is why experimental wet lab biology is just like wild and
Yeah,
like
yeah.
really challenging. It's definitely both. Like the hands matter, right, in terms of like making the sample.
Mhm.
And then it's totally the case that like some protein complexes are just like really sticky. They kind of they adhere to the air water interface. The images just look weird and like there's a lot of kind of sample preparation challenges that are very kind of system specific. So in that way, it's similar to X-ray crystallography, where you just need to like do brute force guess and check to get your protein to crystallize.
Mhm. Do you think we'll ever live in a universe where like cryo-EM and like maybe NMR will be the only determination methods that anyone does, or will there always be a place for X-ray?
Oh, I think there's always going to be a place for X-ray.
Okay.
Yeah. Yeah, I think like cryo-EM is very good at large complexes, and the sample prep is easier because you don't need to crystallize. But if you want to do, like rational-based kind of medchem-driven, structure-based drug discovery, you probably just want to like crystallize your protein target with your small molecule.
Oh, there's no like even like if we had the greatest whatever version of cryohydra in the world, it probably would not be able to resolve the small molecule.
It's not the best for small things because the smaller the target, the less signal you're going to get because the less kind of electron scattering you'll get from the microscope.
Has there ever been a paper that has tried to actually detect whether you can find a small molecule from a cryo-EM image?
Yeah, so you can definitely solve small molecule structures. It just becomes literally exponentially harder because you need more and more data to get higher and higher resolution because you're just fighting against the noise, and there's an exponential decay in the signal as a function of resolution or frequency. So you just need more and more data to solve like higher and higher resolution structures. So if you really want to see kind of like atomic level detail of small molecules, you just need like a ton of data.
Okay, so we went through like ab initio, reconstruction, conformational heterogeneity, compositional heterogeneity. I think an interesting quirk of perhaps like all of the models that you created is that there is not a single universal pre-trained model for any of this. They are rebuilt for every new protein that comes in. Why? Why? Like that just feels alien compared to most machine learning problems. Why was it initially formulated that way when you first came up with the idea, and why has it stayed like that?
Yeah, I think that's a really interesting question, and it is very different from the rest of BioML, right? Where you have like a large, maybe pre-trained model that you can now like AlphaFold, you train on the PDB, and now you can use it to predict new structures. And in cryo-EM and these like cryodragon-based models, we're always training a new model from scratch. So when people are like analyzing data, it's some structural biologist who's like training this like deep learning model, which is super cool to analyze their data. And there's like two things. One is like we're always the problem is that we want to infer the structure. We want to infer like we want to solve this inverse problem of what is the actual structure from the experimental data. So it's very much kind of this like active problem of like kind of inferring the signal from the experimental data. And yeah.
I guess like instinctively, surely there's translatable information from one protein structure determination problem to another protein structure determination problem. Has anyone tried to build like a pre-trained foundation model for all of this, or like maybe they have and it just doesn't work that well in practice?
Yeah, I think there's definitely aspects of the problem that make it really hard to train like a general model. The first is that the images are extremely noisy. And so we're already trying to do this like very hard kind of inverse problem of what is the 3D structure given like these noisy 2D images. And kind of traditionally, the field has been very averse to bringing in prior knowledge because then you can really easily trick yourself.
Yeah, okay.
And the thing we're interested in is solving the new structure, right? We're not interested in pattern matching existing structures. And so because of the high amount of noise, you can really easily just overfit to noise, align all the noise, and get whatever you want from the data.
But I would imagine like protein people would have said that also pre-AlphaFold. Is it like how real is the paranoia that you may potentially like hallucinate some part of the electron density that doesn't actually exist?
So I think it comes back to what is it exactly that you want to get out of this experiment. Like, what is it that you want to get out of this like multi-million-dollar microscope? And there's definitely like, I do think something our group is working on are these like kind of generalizable models that can actually learn across data sets. It's a very hard problem. It's like unlike any other domain of machine learning. So I think it's like interesting to work on. It has all these caveats of all these disclaimers of like, okay, if you do this, the prediction from maybe this like AlphaFold informed like reconstruction model is it actually the structure from the data, or is it a structure from this like extremely knowledgeable prior that knows everything about proteins that, that currently that exists in humanity? And I think it's more interesting to be sure that this is what's in your data.
That's fair. Like, this is like so expensive, so time consuming that whatever the output of it has to be correct.
Right. And like, why else are we spending millions of dollars on these microscopes? Like, just tell me where the atoms are. Like, don't tell me what AlphaFold like kind of already knows.
Yeah.
And I think from like the discovery, from the actual scientific perspective, that's where we can discover new things that we don't know currently about structural biology or protein structure, maybe like antibody CDR loops, things that like AlphaFold can't predict, or these structure prediction models like can't model that well. So the whole promise of structure determination is to be able to determine these new structures. And so the generalizable kind of foundation models for cryo-EM, I think, would be very useful for speeding up the process, and would be very useful as like, I think it's an interesting research direction, but I'm very much of the mind that, we want to let the data speak and to let the data show like experimentally what's going on with these proteins.
I'm not sure how much you'd be able to talk about like what you think the next generation of methods would look like. But if you have any insight into like where things will go beyond Hydra and Cryo-Dragon, I would love to hear your thoughts.
Yeah. So I do think it's interesting right now that there's a lot more methods for heterogeneity, and there's a lot more kind of like deep learning approaches that have different kinds of architectures and different kinds of like maybe inductive biases for the type of heterogeneity or things like that. I do think at this moment, this like heterogeneity problem is very heterogeneous. And so it's kind of dependent on like what people want to get out of the experiment.
Sorry, what is that? What do you mean by that?
Like, do you want, like, right now there's all these different, now we have this like potpourri of different methods. You can get kind of atomic, like maybe dynamic atomic models. You can get kind of like simpler, like linear subspace methods that will give you maybe like larger scale motions. So I guess at this point, kind of what I tell, I guess, like the cryo-EM community is that now people have a lot of choices, right, in terms of like what reconstruction methods they want to use. And so it kind of is on them to understand what the priors are in these different methods. Like, is this a method that only models conformational heterogeneity? So if your data has any compositional heterogeneity, so these are like mouthfuls, then you're gonna
it's
like
easy to
have
like
a
shoot yourself in
mismatch.
your foot.
Yeah. So maybe we're in this like risky time. I don't know.
Maybe like that lends itself well to the question I had, especially while I was writing the cryo-EM article. How much use do these methods have today amongst like non-machine learning, like people who they don't really believe in machine learning at all? Their job is protein structure determination. How much do they use stuff like Cryo-Dragon?
Yeah, that's a great question. So I'm always like delighted when people are actually using these methods. And there's the kind of cryo-EM methods community and machine learning community, which are actively working on new methods, and that's like maybe more cutting edge. And then there's this like much, much larger community of like actual practicing structural biologists. And I would say there's definitely overlap in the methods, but it takes longer time to adopt. And like something that I am very, I guess, like satisfied with during the whole Cryo-Dragon development was actually the educational part of like when we're training these like deep learning models and learning this low dimensional latent space describing different conformations, like what does that even mean, right? So there was like a period just going on like speaking tour and like talking to a bunch of like research institutes and research groups to tell them just like how these methods work, and that they're not like magic, they're not hallucinating things. There's art to training them for sure, but like how do you even interpret the outputs? So I would say they are used, but there's for sure a challenge in terms of like just like understanding the outputs of these models and like really taking advantage of them to extract all you can from your data.
I don't know too much about the culture amongst cryo-EM people, but I know a little bit about the culture amongst medicinal chemists, and it
Hmm.
seems like molecular simulation is really useful in that area. But if you are doing molecular simulation in medicinal chemistry, you're usually like a pure computational chemist who like
Hmm.
thinks and breathes computational chemistry.
Hmm.
And if you're very much into like doing things in the real world, you don't know how to do molecular simulation at all.
Hmm.
So like there's one group at the company devoted to just pure molecular simulation, another group devoted to like giving results
Hmm.
to the molecular simulation people. I guess this is all to like stand up the question of amongst the people who are active users of this model of these techniques, how often is it that they need to like deeply understand machine learning and that
Hmm.
they are kind of been brought up in the culture of computation?
Yeah, I think like there's like two ways. Like, I mean, I think this like bifurcates. If the methods get good enough, like if the models get good enough, then it becomes truly democratized, right? And then you don't need to understand how they work.
Mhm.
And you can just like black box it, use the methods, use AlphaFold, look at the outputs. And as long as you like kind of know enough about like how much to trust it, then it's great. Um, and I think that's like for sure a direction that's worth like going towards, like having robust enough models that with like reasonable default that people can just run and like not need to bother themselves with like all the details of how it works.
Mhm.
On the other hand, if you like there's like if you understand how these models work, you can get so much more out of it, right?
Sure.
You can like kind of debug, you can really get a lot more out of your data. And so I do think right now, like, I hope that people are in this place, and maybe these days with like AI based tools, it becomes like a lot easier to learn about like all these different kinds of like areas that one needs to be kind of adept in to use these models. Um, but I think cryo-EM and structure determination is still very much an area. It's a niche
Yeah.
where you need to deeply understand so many different aspects of this pipeline, like vertically. And if you do that, you have this superpower.
Mhm.
And I think that's still very much like, where we are. And I think like maybe that limits like the accessibility of the method, but I think it's where you can actually like make magic happen.
What do you view as the biggest barrier to adoption? Is it entirely just education, the model is getting better, or
Mhm.
some like secret third thing?
I think it's definitely usability is huge, and also kind of uh, like interpretability of the output.
Aren't the outputs like immediately interpretable because it's speaking the exact same language as the practitioner? Like, what's the interpretability?
I think I mean, yeah, this is like, so now that we live in this world where you can reconstruct these molecular movies,
Mm.
the challenge is now what? Like, what do you do with the molecular
Mhm.
movies? Like, how do you actually then analyze the ensemble? And depending on the question that the structural biologist is asking, then maybe they just need like the two end states or something, or maybe they actually want the movie. But I think like this is actually where it becomes perhaps overlapping with the MD community just in terms of like the way they analyze the ensembles. But like, how do you extract the insights from the distribution of structures?
Yeah. I mean, I guess you alluded to this earlier about how there's like currently a potpourri of methods, each with their own biases and failure modes.
Mm-hmm.
Do you think we're slowly tending towards like a Boltz-esque or AlphaFold 3-esque era where there's a single model that does it all and it's like push button?
Mm. Um, Maybe the field is moving a little bit towards that because of the software packages that exist.
Mhm.
So I guess the other thing about whether people use the models or not, and I think this is probably true for like computational biology in general, is if you want people to use your methods and tools, they have to be easy to use,
Sure.
just from like actual like UI perspective and like kind of software design
Mhm.
perspective. And so right now we're trending towards like these universal tools based on the ones that are actually easy to use
Mhm.
for like people who don't know like how the command line works and
Yeah.
things like that.
Do you
Yeah.
think where the CryoDragon software package is today, it is easily in like people who have never used like GitHub before can like
Hmm.
just use it just fine?
Hopefully. I think, yeah, so I think that was definitely something that I cared a lot about is the usability of the tool, and I have gotten good feedback on it, but it's still a command line based tool. It's still training a deep learning model. And I guess on my end, I had to learn so much cryo-EM to get into cryo-EM. There's like so much jargon in this field. There's so much things to know. And so like, yeah, I think like, and I think it's a good life skill to force these structural biologists to learn like command line based tools,
Yeah.
or to learn maybe like Jupyter notebooks or like Colab notebook based kind of things. And so I'm like, I think this is like a win-win.
Is there like, are there some niches even within cryo-EM that there are no useful like deep learning tools available for today? And it's like, it is very much like, it's like the art that, like whatever they've been doing for the last 30 years, it's probably the best thing.
That's an interesting question. Like neural network based models have definitely like taken over a lot of parts, have eaten a lot of parts of the kind of computational pipeline, but definitely not all. I think the image processing pipeline, there's like a lot of different stages, and a lot of them are just like simple, like function fitting classical tools. And there are parts where neural based methods have like particle picking is one where it's still very much a hard problem to like identify the protein within the larger micrograph, the larger field of view.
Like what part of this ice image actually contains the protein?
Okay. Yeah. So like when you put your sample in your microscope, you take a picture, and so the picture is called the micrograph, and there's like kind of depending on the concentration of your sample, like all the individual particle images of your protein floating around in the ice. And then you have particle picking algorithms, basically like segmentation algorithms that detect the locations of the particles and segment them out for this 2D to 3D reconstruction problem. And that's kind of still a very hard problem. You have like kind of very immediately, there were these computer vision based, like ConvNet based tools to particle pick. There's still like classical, just like cross correlation template matching tools that are used. And, depending on that particle picking algorithm, do you see the rare views? Do you see kind of the rare conformations? And that's still kind of a hard problem. And so people are using like all these different tools, but definitely just like going back to the data a lot to reprocess. And
Well, I guess the way that you're phrasing it right now makes it sound like the simpler methods work fine. Is that the takeaway, that like deep learning, or like the inclusion of deep learning here, has not yet demonstrated like extraordinary results beyond the usual ones? Is that fair to say?
yeah, I think there's it depends on, there's like pros and cons. So like the deep learning based tools work, but they require like a little bit of fine tuning actually, or you need to like retrain a new model every time. And actually, like these days, the microscopes are super automated, are really fast, and the image processing is now like a huge bottleneck in terms of solving structures. And so if you want like speed, you just use maybe the simpler based tools.
Okay. Sorry, go ahead.
Oh yeah, just like the simpler tools.
The one other question I wanted to ask was like, beyond machine learning, how much innovation do you expect to happen in like the physical processes of collecting the data?
Yeah, so that's also very much still like actively being developed in the field. So like people at Berkeley working on these like crazy laser phase plates to just fundamentally increase the amount of signal in the collected images. And that will just like solve all the downstream problems. Like if we could magically get like less noise or be able to irradiate our sample with more electrons before blowing it up, then that solves like all of our downstream problems. So that would be great. So people are very much still working on like the hardware, which is why this field is so kind of like rich in terms of the different like areas that you need to kind of understand.
I was gonna, like, if someone is at OpenAI and working on pre-training, maybe 3 years ago, all they needed to care about was like, oh, how do I distribute my data across multiple GPUs better? But now maybe things are getting so close to the edge of what's possible that they now need to start like deeply understanding CUDA kernel. They need to start like paying attention to every software update that NVIDIA churns out. how much do you personally like stay on top of like the hardware innovations that's going on?
So I try. Like, I think one of the privileges of my job right now is that I can do the research, but I also, both get access and can like talk to all these people in all these other areas. And I think it is really important to stay abreast of all these other, I guess, like directions, to understand which ones like will, completely change our field. Yeah.
When I look at the field of at least like protein structure prediction, it feels as if to me there is not much room left for machine learning advances. And like most of the innovation will just come from like being able to like collect the data better and faster.
That's a hot take.
Well,
kind
like,
of.
yeah, sure, like potentially it's like it's wrong. But I'm curious on like your side,
Yeah.
how much like quote unquote alpha do you think there is on improving like churning the ML crank faster and faster versus just like trusting the people at like Berkeley will like solve the problem by better data collection? Like how much room is there
Yeah.
left to go with like stuff like CryoDragon?
I see. I think there's still lots of like interesting moonshot problems on the ML side. And I mean, like one of the main directions that we're interested in is, can we kind of innovate on the algorithms enough to be able to change how data is collected, right? So like one major trend of the field is moving towards less pure samples.
Yeah.
So before it was like completely pure, and now with like kind of Hydra and these kind of like extreme compositional heterogeneity, we are moving towards like kind of dirtier lysates or just like cellular fractions or like the in situ slices. So that's definitely a trend, and that's only going to be possible if the algorithms can either keep up, or can the algorithms themselves motivate new ways of collecting data.
I think it's like all my examples are coming from the protein structure prediction field, but there has been, I think it took a few years post RF diffusion being released, I actually saw for the first time that like, oh, these models have given us research papers that otherwise, like clinical stage research papers that otherwise could not have existed if this model did not exist. Are there some cryo-EM determined structures out there that exist and are deposited that you suspect would not have come about had stuff like CryoDragon not existed?
Oh, I don't know. I feel like it's like too like,
I guess it's a strong claim to make.
yeah, it's too strong of a claim to make. I mean, in the the hope of these tools is yes, right? Like, and in the original publication, the satisfying part was kind of reanalyzing previously published data sets and finding structures that were missed.
Okay, that's something.
So that was awesome. Yeah, that was super cool. Especially because like at the time, I didn't have like the taste to like understand what I was doing in terms of like reanalyzing the data. And I was like, oh, this is weird. I guess it was not there. And then it was like, wait, this was not there before. That's cool.
Yeah.
So I think that was, I guess, like super gratifying.
Going back to like when you like began in this field entirely and you need to like come up to speed on cryo-EM and like all the jargon that entailed. What was the biggest like almost like culture shock that you had coming into the cryo-EM field versus, I'm assuming like you were primarily like a physics ML person prior to this?
Well, I was actually an MD person, or like molecular dynamics person
yes.
prior. So yeah, very like new to cryo-EM. And I talk about like so there's like kind of a bunch of like mathematicians working on the cryo-EM problem, and those papers are like, a lot easier to read because there's less jargon. So that was maybe like my initial foray, but then, just like reading all the papers in the field and just like trying to like make sense. The jargon was like the biggest shock originally, just as like a kind of graduate student, like, trying to like figure things out. My first time actually talking to like kind of meeting people in this field was also just like interesting in terms of, I guess the jargon was the main thing. I'm just like, okay, what is pseudo symmetry? Like, is it symmetric or is it not symmetric? Like, what the heck is pseudo symmetry? And so like I remember one of the first times I gave like a talk on CryoDragon to a primarily structural biology community, they were really kind of suspicious of deep learning.
Yeah.
So I think there was a major sea change in, I guess, the structural biology community because of AlphaFold.
Okay.
So that was like a pretty kind of major shift of like a vibe shift of whether people trust kind of deep learning based approaches or not. And so definitely before that, there was a lot of kind of skepticism, but there was a lot of excitement too, because heterogeneity was like the next frontier of like, how do we like of the technology and how do we model continuous motions? And so I think, yeah, in the beginning, people were extremely excited, and I was trying to like not overhype it, you know, of just like, don't get too excited.
Yeah.
This is like, it's not going to solve all your problems. Like if it's garbage in, if your sample is like really, really challenging, it's not going to like necessarily solve all the problems.
Do you
Yeah.
often find that, at least in the, actually, I'm not going to make any broad statements about proteins again. At least within like your group and perhaps other cryo-EM ML research groups, how much of the innovation comes from like talking to cryo-EM people and listening to like their ideas and like, yeah, their research ideas versus looking at like the ML literature. Like it's like I think, to take a concrete example, there feels like a pretty strong connection between your work and like the NERF work, like the neural radiance fields. Like how much of it is that where like you're taking inspiration from the ML literature versus taking inspiration from traditional cryo-EM literature?
Yeah. So I think now we want, like, I think my group has people who are, you know, very much like computer vision, machine learning people, computer scientists, kind of people who are more mathy. We have a biochemist, physics, biophysicist. So I really love how kind of interdisciplinary or multidisciplinary the group is, because you need to draw from all these different kinds of areas. Originally, CryoDragon was like, I had no idea about NERF. And so at some point, and CryoDragon preceded NERF. And then when I saw at some point somebody was like, oh, you should check out this like neural radiance field. I was like, whoa, that's like super cool. And I had no knowledge of like computer vision. And I remember my PhD advisor at the time being like, oh, you should like think about whether this type of architecture can be useful for like other domains. I was like, ah.
You could have been a graphics researcher.
I could have done graphics.
Yeah.
So I guess like there are like, and I sense, yeah, definitely like it's good to stay abreast of what's going on in machine learning. What are the trends? What are the latest and greatest like architectures and like kind of training paradigms and like activation functions and things like that. But I think it's extremely important to stay focused on the problem at hand and focused on what are the challenges associated with a specific problem and like whether the kind of techniques can be like cargo cultured or not. And most times they can't, but you know, like related things. Yeah.
So I'm assuming like you aren't going to like SIGGRAPH every year to see like what inverse E problems people in the graphics field are working on.
No, I've never been to SIGGRAPH, but I sometimes go to the computer vision conferences. And I think it's like nice to establish crosstalk between all these different communities because the problems are so related. But yeah, the kind of thing to fight against is the, you know, kind of just chasing the trends in these other areas and applying them to cryo-EM or, yeah, like, I don't think that's the way to go about it.
Outside of particle, like applying machine learning to particle analysis, you mentioned that there are machine learning being applied to like actually like picking the particle itself. What do you view as like the most promising direction outside of particle analysis? Is there anything that you view as particularly interesting outside of like what the Alan Zhong lab is working on?
Oh, well, I was gonna interpret your question as like outside of the 3D reconstruction problem.
Sure. Yeah. Exactly.
Yeah, and which is also something that our group is working on right now. But outside of, so like really we've been focusing mostly on this 3D reconstruction. So just like 2D to 3D kind of image processing. The kind of direction that we're getting into now is this cryobolts paper. So with the atomic modeling. And I think that's something that's really interesting. It's an unsolved problem. It's largely done manually still. It's unclear how to do it for low resolution maps, but how do we actually build the atomic models into the cryo-EM density volumes? especially when we have a ensemble or distribution of structures from CryoDragon. That's currently unsolved. How much should we rely on priors from like structure prediction models when building in the atomic models?
How much do you personally trust them?
I think we should use them. We should definitely kind of use them for everything they got.
Mm-hmm.
I think now the challenge is validation. Like once it spits out a structure, how do we actually validate at scale if we have like a kind of, 1,000 cryo-EM volumes that we're kind of building atomic models in? How much information do we share across those 1,000 structures? And now how do we automate the validation procedure? Because any like practicing structural biologists, when they deposit an atomic model, they're going through every single residue or every single atom, like residue by residue. And yeah. So should we still be doing that?
Yeah.
That's an open question.
Earlier when I asked about like why aren't pre-trained foundation models using cryo-EM, you said like you want to actually like recapitulate the data as you measured it and not potentially hallucinate something. But it does sound like if you're going in the cryobolts direction, you are potentially like it is on the table to hallucinate something.
Yeah.
How much have you seen that happen in practice?
That's a great question. I think one kind of, I guess the way that I'm approaching it right now is separating the reconstruction problem from the atomic modeling problem. Okay. People are definitely trying to bring them together and having like reconstruction models that are like deformations of an atomic model. And that's where I think you can get hallucinations. And I have seen there was this really interesting kind of case study that one of our collaborators at Princeton showed us, where if you have a homogeneous data set, so a synthetic data set, you can create a synthetic data set of just a static structure, and it's extremely noisy. And if you fit one of these like heterogeneous reconstruction models, you hallucinate conformations, especially if it's one of these models that only model conformational heterogeneity. You just get like these fluxing motions that are definitely not in the data.
Yeah.
And so, yeah, that happens. Right. And that's something that, is worry.
I actually hadn't mentally separated this like 3D volume reconstruction problem as like something you do first and then you assign like residues. I assumed, I guess like now like, looking back at the actual papers, it does seem like there are two sequential steps.
Yeah.
Is it obvious? Like going back to protein, there's like a similar question of like, should you design the structure first and then the sequence inverse, or maybe you do both at the same time? And the canonical thought has always been like, oh, you want to design them at the same time because they kind of like rely on each other. Is there like any similar like undercurrent of thinking within the cryo-EM field where you want to be able to do both at the same time because it just helps you succeed at each of them individually?
Yeah. So I think like by separating them out, you are separating kind of the 3D structure determination from the sequencing of the actual protein. And like, obviously, maybe you needed to like sequence something to make the sample in the beginning, but not necessarily, especially if you're just extracting from the wild.
Yeah.
And so it's been used like cryo-EM has been used in this like bottom-up fashion just to discover new proteins, to discover new complexes, new interactions. And then it becomes a hard problem of like, how do you sequence the thing that you've solved the structure for? And I think, now in this like post AlphaFold era where we have like structural hypotheses, it becomes less of a kind of like completely crazy problem. But I think that is one of the exciting things. And then in an actual design context, you could imagine like high throughput structure determination of like a ensemble of different design sequences and then seeing afterwards which ones bind or something like that.
Yeah. How much, actually, this is a question I probably should have asked a long time ago, but when you're actually assigning atoms to this three-dimensional model, how often is it the case that you know what residues are on the table to start off with versus you don't know anything about the sequence?
I think most of the time you're trying to solve the structure of something whose like sequence you know.
Okay.
Yeah, you want to determine this like new protein structure. This is the sequence that you've like purified out. But especially if it's from kind of like an endogenous source, you never know like what else is going to be there.
Yeah, I imagine
Like
for like
whether there's like
lysates, this is,
ligands or if it's from a lysate, like whether there's like ligands bound, whether there are other kind of co-complexes that are or other complexes that are co-purified. And so that's the thing that from the machine learning standpoint is like an interesting maybe like axis is like how much do you rely on priors and how much do you kind of allow for discovery.
That makes sense. And I know that you posted on Twitter a while back that you recently took a sabbatical from Princeton to be at Generate Biomedicines for a bit. And I learned this morning that sabbatical has now ended.
Yeah.
What were you working on there? And I guess, sorry for,
awesome.
So for some context, Generate Biomedicines bought this 70,000 square foot facility, I think in 2023, and just filled it with cryo-EM machines. So like clearly there's like an overlap as to like why they actually like need your exact skill set.
Yeah.
What were you working on there?
Yeah. So at so that was an amazing sabbatical. So Generate has 4 cryo-electron microscopes, which is double number of Princeton University. And all these challenges that we talked about in the past of like, okay, the data sets come from like all these different like research groups around the world. I mean, they're aggregated in these databases, but like the quality is kind of different. At Generate, that's a place, like that's a single organization where they're very much where they can, actually standardize everything and like pipeline everything for high throughput structure determination. At Generate, we were working on structure determination and kind of solving the ensembles of antibodies.
The conformational.
Yeah, the conformational ensembles of antibodies and trying to like ask interesting questions about the role of kind of antibody structural dynamics in binding, in kind of affinity maturation and things like that. So that was super cool, but very much from like a, like, can we just actually observe, right? So like CDR, I learned a lot about antibodies. It was amazing. But yeah, so the like kind of, is there like a logic or grammar to antibody CDR loops?
Why, what's the utility of structure there?
Yeah, great question.
Because like in my head, CDRs are floppy. Is that just like completely incorrect?
Right. In my head, they are too, but no one knows,
Okay,
right?
yeah.
Because no one's observed the floppiness because we haven't had tools to be able to observe conformational dynamics or conformational ensembles until, I guess, cryo-EM. And it's still very much a challenging like sample prep problem, especially if you're trying to scale it up. But now can we actually just like observe from experimental data what the actual floppiness of the CDRs are? Is that actually the case, or are some more rigid than others? What's the sequence determinants of that? And obviously there's like lots of therapeutic relevance if you understand like kind of if you can now rationalize the structures of the loops.
How much are you able to share about how floppy they actually are?
Oh, well, very much still a work in progress, but it is publication oriented, which is why I'm really excited.
Gotcha.
And definitely kind of, why I was interested in doing the sabbatical there.
What is the clinical relevance? Like let's say you are able to determine that, the CDR loop is floppy, it binds in this specific way. It's like, what do you tell a therapeutics team? Is there like the result of this process?
Yeah, I feel like what kind of, or the therapeutic angle is like above my pay grade or outside of my like actual area of expertise, but I would imagine that the floppiness has some functional relevance. And like if you can better understand, characterize, or design the function of the binder, maybe you would get like fewer off-target effects, or you would, just actually have like more useful functional data about your antibody or about your therapeutic.
Did the experience make you like desire building therapeutics? Or like did you go the other direction and think like this kind of sucks?
Yeah, no. It was extremely inspiring. I would say my prior has always been more on the academic side of like, like basic science. There's so much we don't understand about biology. I think working more like upstream on the fundamental things is like more, I don't know, just like interesting. And then actually being there and realizing that these are like real drugs that are actually helping people was very inspiring. I was like, oh, yeah. So that was cool. That was super cool.
The when I saw that they acquired all of these cryo-EM machines, I did not know it was only four. In my head, it was like dozens. But
4 is a lot.
four seems to be a lot. Um, my initial thought was like, oh, they want to like they're the ones who made that protein structure model Chroma.
Mhm.
Maybe they want to scale up protein structure determination using these. Was that also on the roadmap, or is that like, yeah?
Yeah, I guess like so I've known some of the people at Generate for a long time. I think like Gregorian, the CTO, John Ingraham, the head of ML there, like they've like their papers I read when I like started as a PhD student was like, whoa, these are like super cool like protein ML papers. I think their hypothesis, okay, who knows? I don't know, but like I think definitely structure prediction is like a huge kind of capability, or like generative models over protein structure. And then can we use those models for design? But obviously, can we kind of like, I think very much this area, you don't want to stay purely in silico, because if you actually want to make real therapeutics, you want experimental data, ideally in high throughput. And so I think probably cryo-EM was like a major part of that.
Yeah.
And that, that investment was like long time. That like was very, what's the word? Ahead of its time, I would say.
There's one other therapeutics company that has made a really big bet on cryo-EM. I think it's Gandiva Therapeutics. Do you happen to like know what their particular bet is?
I think there's a couple. There's definitely others that I'm aware of that are using cryo-EM. And I think the idea there is very much to use cryo-EM to understand maybe like cryptic pockets, or I don't actually know about Gandiva in particular, but just like my understanding is like with cryo-EM, you can actually get the ensembles. And with the ensembles, you can maybe find new binding sites, or better understand like allosteric mechanisms and things like that.
You've done a few things besides cryo-EM as well. I'm going to talk about one thing that your like future work is going to be focused on, and one thing that your past work was focused on. The future thing seems to be cryogenic electrotomography.
Yeah.
The basics of the technique, I think, is just like exactly the same as cryo-EM, but you're like tilting the sample, so you get. Actually, maybe it would be best if you explain it.
Yeah. So cryo-electron tomography, or cryo-ET, is using the same microscope as in single particle cryo-EM, but there's two main differences. One is the tomography part is now, instead of just taking a single kind of projection image through your ice, you're now tilting the imaging stage, like plus or minus, I guess 60 degrees is practical, and taking a series of images at different angles. And so then you kind of get a 3D kind of tomogram. And so you can see things in 3D. And so that's one main change, is the tilting. The other change is that it's usually used to image like in situ samples. So like thin cellular sections. So instead of like a purified solution, you're looking directly in situ.
Like, sorry, I guess that maybe answers my follow-up question of like, can you not approximate this three-dimensional view from cryo-EM? But like, I guess the in situ part demands that like each molecule is like unique, and you're not going to see it repeated across the entire data set.
Yeah, so the like spatial scale is different. So now you're seeing kind of like subcellular architectures and like kind of membrane, like morphologies, or like organelles and things like that. You can still identify individual particles and then pick all those particles. And it's like the individual particles are like super noisy and super low resolution, but you can do the same trick as in single particle cryo-EM, combine them all together and computationally like amplify the signal to get near atomic resolution structures in situ. And so the extremely exciting part there is that now we're determining the structures of these protein complexes instead of like in a crystal, which is like from X-ray crystallography, or instead of like in a purified solution. Now we're actually looking at the functional structures in
like the native environment.
In the native environment.
One instinctive question I have is,
And you also get the spatial organization too, which is super cool.
how large are these samples usually? Are you able to like see them with your naked eye?
Hmm.
Or like,
No, so I think the field of view is still pretty small. So
okay.
there's like many orders of magnitude between like kind of angstrom scale things that we resolve to maybe like nanometer, hundreds of nanometer scale, like kind of sections to like whole cells,
Mhm.
right? And like definitely um, whole cell visual proteomics is like a huge like kind of research direction for the field.
Mhm.
Can we like have those beautiful David Goodsell images of these cellular landscapes, but from experimental data?
Yeah, I was gonna ask, like, how far are we away from being able to image an entire cell at
Hmm.
once? Has that already happened?
So that has already happened. It depends on how big the cell is. Yeah. And so people have done this with like bacteria, which are much smaller, but for larger and like, yeah, more complex eukaryotic systems, uh, it'll require a lot of data. And then it's kind of an interesting question of like whether you want to be like hypothesis free about it and just like see all the things, or whether you want to like test a specific hypothesis and like, have like with a drug, without a drug. And I think that's like a kind of challenge or maybe like a research question for the field.
What's an example of like a hypothesis-driven question you'd have about a cryo-ET result?
Hmm.
Is it
Uh,
like does this particular protein exist in this native environment, or is it something like coarser?
I think people are interested in kind of like personalized medicines, right?
Okay.
So like, does the morphology of some organelle change? Um, and so it is tackling kind of this length scale that's unique, right? Light microscopy can only get you so far. It can only get you the wavelength of light, which
Yeah.
is like thousands of times larger than the wavelength of an electron.
Yeah.
And so with cryo-ET, you can actually see maybe like subcellular kind of features and architectures. Um, and then, like for certain complexes that are abundant, you can get like molecular details and like atomic details. And so, really, the dream would be able to span like all these different length scales from like atoms to cells. Yeah.
The idea of a cryo-ET result being clinically relevant is interesting. I don't think
Mm-hmm.
I've ever heard a claim like that before. Is there like some particular disease you're aware of where like if we could exactly measure like the physical structure of like the mitochondria or something,
Mm-hmm.
that would help a lot? Or is it kind of like a basic research thing where we're not sure how this
Mm.
will help?
Yeah. I am not sure. I feel like there's probably scope, but it's like way above my or I don't know enough about kind of the clinical side of things.
Hmm.
It is an expensive uh like experiment.
Yeah.
So I think that's one of the main challenges is like the facilities, it's like expensive, it's hard to do, it's immature still
Hmm.
in terms of like, you need like a lot of um like the sample kind of preparation and everything is very much like still like people are working out how to do it most effectively and efficiently.
So it's like it's a newer method than
Yeah.
cryo-EM. Okay. Is it do you imagine it's like the road to getting more traction is there? Like it's already shown like really early promising results. Maybe
Hmm.
like cryo won the 2017 chemistry Nobel Prize.
Hmm.
Is this on track to win the 2025 Nobel Prize?
Hmm. I have no idea.
Or
That I have no
2030?
idea, except that I do think because it has this unique vantage point in this like length scale of, I guess, like cellular and molecular biology, it really spans molecular and cellular biology. It can be used to like find new
Mhm.
things and make kind of really important discoveries for sure.
Yeah, that
Yeah.
makes sense. I another thing you mentioned to me just when we were talking this morning is that you
Hmm.
are also working on NMR, which
Yes.
is new to me.
Yeah.
What are you doing there?
Yeah. So that's been super exciting just from kind of like a personal level because I've been working on cryo-EM for a long time and there's so much more to do there. There's a lot of really interesting kind of open research questions. But we do have a new direction in the group that is small molecule structure determination.
Mhm.
So I guess that's the commonality is like, can we just like do useful things and like help chemists? Now we're talking to chemists. Can we help chemists elucidate the structures of novel natural products and like novel kind of like molecules that is still very much bespoke kind of method. Done manually, requires like expertise to just like stare at these NMR spectra and figure out what the graph or the structure of the molecule is. So yeah, I think that's like a super interesting. When I first learned about that problem, I was like, ooh, I had the same kind of like feeling as like the cryo-EM problem of like, this is a really cool problem and I'm not aware of anybody else working on it right now. And this seems like a really useful problem to solve.
So the mental framework I have, like the mental framework necessary to understand cryo-EM was a little bit alien to me when I started reading about it. You have a bunch of these two-dimensional images from an electron beam passing through a protein. You have an electron detector that records the signal, and your job is to reconstruct all these 2D images into a three-dimensional structure. What is the mental framework for applying ML to NMR?
Yeah, so it's another, I guess, like it's another inverse problem where we have like imperfect experimental measurements. The spectra itself is like, the like NMR or the shift of the resonance of these different nuclei, either like protons or C13 or carbons, isotopic carbons. And depending on the shift, that tells you about the local chemical group and the local chemical environment. And then the like puzzle that usually like a human, like a kind of expert will do when they're looking at the spectra is like, oh, there's a peak around here. So I know that this is like this type of hydrogen in like a benzene ring or like this type of hydrogen. And there's a peak around here and there's like some J coupling. So it must be like kind of near some other type of chemical group. And maybe like the chemical formula, like you've done like mass spec or something. So kind of like the total composition of the molecule, but you don't know at all how it's like kind of connected together. And then from the spectra, you just like stare at it. And from, all of your training, that these peaks are artifacts. These peaks should be there, but it's missing because this always happens. And so when I learned about this problem, I was like, oh, this seems perfect for machine learning. I guess what was most inspiring to me in the beginning about, I guess, this like area of natural products is like, if you look at the structures, well, one, they're like oftentimes the most kind of bioactive and like therapeutically relevant molecules. They're isolated from natural sources instead of like made from kind of like in like rational drug discovery or like these like kind of drug-like molecules. And they look crazy.
Yeah, I've heard this from natural products.
If you actually read the papers and look at the structures, I'm just like, oh my God, these molecules are like gorgeous and also like totally gnarly. Like they look really exotic. And I'm just like, this is what the bacteria are making when they're conducting chemical warfare against each other or whatever they're doing. And then you read the machine learning papers in like chemistry and it's really interesting, maybe like kind of modeling problem, but most of the data sets are like super small molecules that have like fewer than maybe like, I don't know, 20 heavy atoms or something like that. I'm like, there's a huge gap here in terms of like what we're actually modeling from a machine learning standpoint and like what are the kind of like super cool active molecules that we're just extracting from nature. So that was the main motivation.
I imagine whenever I see a chemical structure of a natural product, like one, it does look often pretty crazy. But like two, how does anyone come up with those structures today? Like in the cryo-EM, when you arrived to the field, there were a bunch of like traditional methods being used. Are there a set of traditional methods also used to determine the structure of these really crazy molecules? Or is it like they need to learn how to synthesize it and then from that they naturally get the structure?
No, you very much like don't know how to synthesize it. So the synthesis problem is usually downstream of discovering and characterizing the molecule and oftentimes like, all these like really kind of, expensive like cancer drugs, they're still extracted naturally because we can't figure out from like a chemistry perspective how to do like the total synthesis. And yeah, I'm not a chemist. I'm just kind of a computer scientist, but I think like natural products is interesting because we just kind of mine nature and like maybe figure out how to perturb these bacteria to produce all these crazy chemicals. And then we just extract them from natural sources and then do all the biochemistry and like physical chemistry or analytical chemistry experiments to figure out what it is and like figure out how it works. figure out how the enzymes that like make it work, and it's just like a whole super interesting field that has been great to like get a sneak peek to last year or two.
I know very little about this field, but I do remember reading these like mass spec foundation model papers from like NVIDIA NVIDIA, if you know them.
Mhm.
And they like claim to be able to turn like the mass spec peaks into the actual structure of the molecule. How much like how trustable are those methods?
Mhm. I think the mass spec stuff I don't actually know that much about. I do think like metabolomics, there's a lot that's an interesting I guess like problem, especially when you have like complex samples and things like that. But from our chemistry collaborators, I think when you're trying to solve the structure of when you're actually trying to solve the structure of a new natural product, you typically use NMR,
Okay.
which gives you more information on the actual connectivity of the atoms.
And so like the mass spec information is like underdetermined for the structure problem. There's like just not
Yes.
enough.
Yeah. I think mass spec is usually used to identify composition or just
Okay.
like identity of like is a molecule there or not. If you already know the molecule, you know kind of its spectral signature.
That makes sense. And so right now I've talked about cryo-ET and NMR, both of which you're working on right now. But for a long time, 3 years, you were at DesRes before going to graduate school. And I have several questions on that front. The first of which is, why start with molecular simulation? Like, why was that the thing you originally were working on when you were at University of Virginia?
Yeah. I would say luck, like originally, how did I get into research and how did I get into the area that I was in is kind of just like luck. And I mean, I'm extremely fortunate to have met the kind of undergrad research mentor I had at UVA. And from him, that's where I learned about protein folding and molecular dynamics. And we wrote kind of this like super cool, or I thought it was super cool kind of model to simulate protein folding. And that's how I learned about Anton and DU Shaw Research. And then I was very lucky to work there for an internship and then full time for 3 years. And so, getting into that area, I think was just luck in the beginning. But I'm really glad I did, for sure.
Do you ever, I think there's a common pattern of like a very smart person who like touches molecular simulation for a few years and then gets out of it because they think like this is like not useful for anything. Did you have a similar reaction, or was it more like, oh, like I'm curious about other things besides molecular simulation?
I think a little bit of both. I think like working at DesRes, I was working on free energy calculations and like binding affinities. And then through that was working on originally like the sampling problems there, which is really interesting technically, and I learned so much. And then after, I mean, like characterizing it on more systems was like, there's a force field problem here. And then worked on like some quantum stuff to like better estimate the force field. I was like, this is a really hard problem. And then was like, okay, at the end of the day, all these predictions need to be validated experimentally. And then I had no idea anything about biology at that time, or experimental biology. And so that was just this like huge area that I was like, that's the answer key. And it's a huge mystery. And so I think after a couple of years, it was definitely like a following kind of what's next and like wanting to understand the experimental side.
Yeah. And were you like a pure physics person by like undergraduate training?
In undergrad, I was doing chemical engineering. And so that's where I was exposed to stat mech and this protein folding area. And yeah, so it's interesting now I'm in a computer science department. I was kind of, I took the CS classes, but wasn't that interested in some areas of computer science, and it was too hard to get into the classes because it was really oversubscribed, and I don't know. I liked chemistry for sure.
Yeah. Do you ever imagine to like returning back to molecular simulation in any capacity, or are you kind of set on this cryo-ET NMR track, and maybe even those like will involve some molecular simulation?
Yeah, definitely. I'm not like against it at all. Like I think especially now, there's so much interest, right, in molecular simulations with neural-based approaches kind of eating various areas of MD. And like, again, it's all about kind of what are the questions that this technique can answer. Like cryo-ET gets this like unique length scale. MD also, I feel like, accesses a unique length scale that you can't get with experimental data, right?
I think, yeah, like I saw this really interesting graphic that says like the timescales of NMR are incredibly coarse to what you can achieve with sufficiently good like coupled cluster. Yeah, sorry, go ahead.
Yeah, right. And like the dynamics, I mean, what originally drew me to the cryo-EM problem was that like, oh, we can actually get the dynamics of these proteins, but from experimental data instead of from like simulating these very, very simple like physics-based models. And so that was super cool. It's like, oh, this is like directly from the data. However, in cryo-EM, the ensembles are still like just like larger scale, slow time scale conformational changes. And so I think you're never not going to get like super fast kinetics from a cryo-EM data set. And so there's like, yeah, there's interesting areas of like overlap or complementarity between MD and cryo-EM.
Have you ever felt like does like anyone in the Ellen Zhong lab focus on applying molecular simulation to cryo-EM? Or it's somewhat of like a nascent field where you're like, you aren't sure where it could actually be applied?
Some of our collaborators are definitely applying MD to cryo-EM right now. Oh yeah, and my lab I call Easy Lab.
Oh, okay.
Yeah, which is a fun acronym. So MD, I feel like it's even more so this like bespoke method. So in cryo-EM, it's like bespoke for each data set, but MD is even more so because there's like this upfront cost of like setting up a simulation and like kind of all this stuff to validate the force field terms for a particular system. So right now we're not directly kind of integrating MD-based modeling in cryo-EM, but definitely using it as like interesting test bed for conformational ensembles from cryo-EM.
During your time at Desres and the subsequent decision to go to MIT for a PhD, what was the primary motivating factor? Yeah, like I do know there is this like track of like scientific associate at Desres to PhD track. Was there anything else that was on your mind of like what you could have done besides?
Yeah, I guess at that time I was, the main motive, I wasn't sure, right? I kind of like not really sure exactly what I wanted to do with my career. But I thought like learning more things would be great. And I think concretely my GRE scores were going to expire or something like that. So I was like, I might as well apply. Yeah, I remember like going through the process, and it was really useful to like think about what exactly do I want to like kind of, what would I want to study for a PhD, and what kinds of things am I interested in? And then after going through that process, it was like pretty clear. And after starting my PhD, it was so clear. I was like, this is really cool. Yeah.
Have you ever gone back to look at your personal statement or statement of purpose and seen how much you've deviated since then? Or is it pretty like spot on? Like, oh, I care a lot about validation. I care a lot about validation today as well.
I definitely remember going back to my statement of purpose just to like look at which groups I was interested in, and it was totally different.
Okay. Because you were not even like super, were you aware of cryo-EM at the time?
No, not at all. So that was only after like a year, my first year of my PhD, after doing rotations in all these different areas. And I tried experimental stuff, which was cool. Like learned how to pipette, which was cool. Did some neuroscience, which was crazy. Yeah, and I was very open to like many different things. And then when I learned about cryo-EM, I was like, okay, this is...
The last questions I had was, if you had $100 million to spend on anything, someone gave you that money, no strings attached, what would you spend it on?
I think I would be doing exactly what I'm doing right now.
Well, sure. Like, not in terms of like, oh, I'm gonna like go retire, but
like I need to spend it or something.
Or like would you go out and buy like 100 cryo-EM machines? Like, is each one $1 million a piece? I'm not entirely sure, but like, what would you be spending that on in terms of like accelerating your own lab?
Yeah, that's a really interesting question. Um, I don't like, I wouldn't change anything about like what I'm doing right now. I think like the problems are interesting, the people, my group is amazing, and like the research, I don't feel particularly limited.
Okay.
Maybe if I had to spend $100 million, like would branch out into like more of the experimental side and like have more data generating capabilities to like either test hypotheses or to like design the experiments. But yeah, I feel extremely lucky right now that like, you know, we get to just work on the cool problems that, yeah, that are hopefully useful.
I feel like that's a rare answer. Usually when like given $100 million on the table, people are like, yeah, I'd like like I'd buy so and so machine that started like so and so research group. And especially cryo-EM feels like the sort of thing that is so bound by the world of atoms. But yeah, like I guess in practice not.
Yeah, I think yeah, I'm thinking like maybe just like concretely, right? Like then I would need to know how to do cryo-EM experimentally or like do NMR experimentally or something like that. And so that's like a whole other thing
Well,
that
actually, I think that's an interesting question. Would you trust yourself to do NMR or cryo-EM independently today?
me personally, no, right?
Really?
Like I have no idea how to do that. Like
Really?
there are people in my group who do collect data and that's great, but I've never collected data.
Is it the sort of
Yeah.
thing where it's like you genuinely need like months upon months, maybe even years of training to be able to do it well?
Uh, Yeah, I think like I was talking about earlier, the field is so maybe like it's so deep. You do need a lot of expertise. And I think there was an opportunity at some point during my PhD to like, actually think about collecting data or something like that. But it was just never, I don't know, like I had, I liked coding too much.
Yeah, that makes sense.
And I think like if I had like it's interesting. I guess money is not really the bottleneck. It's like time and bandwidth. And like what was so amazing about the sabbatical is like, oh, I don't have to teach now.
Okay.
And now I can like code myself again and run experiments and or kind of computational experiments.
Perhaps a question I should have asked earlier is like you were probably one of like the person who made like the particle analysis cryo-EM machine learning field big in the first place. And now there's like entire workshops devoted to the project or to the research field. With the rise of like many more talented people entering the area, I imagine there's also some deluge of like more like noisy, lower quality papers. Is there some easy way for you to tell whether to take a cryo-EM paper seriously or not?
I think I don't like looking at kind of the field with that lens. I'm
Sure.
like, I think everybody is like doing interesting stuff as long as people have like, scientific integrity. And I think people are interested in different aspects of the problem. And I like that we have that flexibility, right? Of like, oh, they're more interested in like proof of concept and are writing kind of conference papers and can get these like concepts out there more quickly. And then there's papers that are more kind of targeted towards users, right? And like kind of actual tools that people will use. And I think as long as there's like a healthy ecosystem that where people have kind of the flexibility to work on like the style of research and, we're kind of making forward progress as a field, then I think that's great that there exists kind of these different types of research directions.
I guess like concretely, I know like especially in both the field that I work in right now and the field I worked in prior, there are like known data sets that are like people like claim very strong things in either toy data sets or known data sets that have really big fundamental problems. I think maybe most overlapping with our work is like I think like Pose Busters is known to be like kind of a bizarre data set. Like it's very easy to achieve.
I've heard this.
Yes,
I don't know why, but
I don't know. I don't know why either. I just I've had
Yeah.
colleagues who say this. I guess like the cryo-EM data set world is a bit smaller than the protein in the small
Yeah.
molecule world. But like, is there any issues like that? Like, actually, instinctively, what I thought your answer was going to be was synthetic data is like really hard to take seriously.
Yeah.
But maybe that's not the case. Is it like you do?
Yeah, I think like the proof is in kind of real data and seeing whether a method works on real data. And there's some like established benchmark data sets that people are usually like analyzing. So that's definitely like one of the, like markers of like, how well does this method work? And I mean, one of the challenges for especially new people coming into the field is that you need a lot of expertise, like domain expertise in interpreting the results and interpreting the structures. One of the things that one of my group members did last year, it was at the NeurIPS benchmarks track, was a cryobench or like a benchmarking effort, which was hopefully designed to like both have simple diagnostic data sets that people can use for methods development that can like tell them like whether their method is working or not from like both like qualitative and like quantitative metrics, and challenging data sets that will motivate new methods development. And so we were very kind of deliberate with like the design of these data sets. And so that's been super cool to see where people are like actually kind of using these data sets and like computing the metrics. Metrics is like a huge problem for the field because, I think that's like one of the that continues to be an open problem for the field. And so, I think maybe the lack of metrics helps guard against, like blindly kind of just like following a number. But I think, it makes it harder for like new people, like maybe who are more expert in like other areas like graphics or vision to get into the field. And so with all these things, I think there's just like, nuance and, it's important to keep that in mind.
Metrics, like what is the story on cryo-EM metrics? Like, is it just RMSD? Is there something else beyond that?
The main metric is resolution for a given volume, but that's also kind of estimated a bit heuristically, and a notion of like global resolution for the structure doesn't actually hold. And the actual computation of resolution can be hacked a bit. So that's like for sure a like challenge in the field. There's enough people who have the expertise to like judge the quality of a structure that like, you'll get called out for it, right? So that's like one of the main metrics is like kind of resolution and computed via something called FSC or Fourier shell correlation. For heterogeneity, for kind of ensembles, it doesn't exist yet.
Okay.
And we have like, some stand-ins that are like FSC based. Some people in our group are taking some of the kind of shape-based metrics from computer vision, like kind of chamfer distance, just like volumetric IOU and things like that. But there's a lot of just caveats and challenges. And so I think kind of metrics for conformational states and kind of measuring what is it that you care about is not solved.
Not like naively, I think. Why isn't the confirmation problem just like, oh, there are these 5 confirmations in the data set. If your model doesn't give me back all 5, or it gives me 4 out of 5, why don't you just report the accuracy? Like, well, like what's the nuance there?
Yeah, I think even like RMSD, right? So that doesn't capture the specific conformational state that well. And I think like, people are using maybe like local type metrics, or maybe that would be a direction to move forward. But that is very system dependent. And so I think kind of a general metric for conformational state just doesn't exist right now. Perhaps against a target data set, you could define something like that.
Was that done for cryobench?
We didn't have a kind of data set specific metrics. That's definitely something that I want to move towards. Like especially one of the data sets is like based on an MD simulation. So there's like 46,000 structures, distinct structures in the data set. And you're not actually going to be able to recover 46,000 distinct structures. So how do you actually characterize the distribution? And you have distributional metrics, right? That is established. But what is the actual what is the representation? Like, there's all these actual details in terms of the metrics and computing distances that can make it.
I think that was
Cool.
the last question I had.
Yeah. Thanks for the conversation.
Yeah, absolutely. I am struggling to think of anything else. Where are you seeing? 1 hour 47. Okay. That's not bad.
Good.
Yeah. Cool.
Awesome.
Okay.
Ship it.